To the ISGAN Academy webinar of today. The title is Optimizing the Value of Storage in Power System and Electricity Markets, the SMart4RES project. Before starting the webinar, I would like to introduce ISGAN that hosts this webinar. ISGAN is the short name for the International Smart Grid Action Network, a technology collaboration program of the International Energy Agency. ISGAN is also an initiative of the Clean Energy Ministerial, formally established in 2011. ISGAN created a strategic platform to support high-level government attention and action for the accelerated development and deployment of smarter and cleaner electricity grids around the world. ISGAN consists of 27 contracting parties. Their nominated representatives form the executive committee, headed by the Presidium, assisted by 2 co-secretariats and the ISGAN operating agents. ISGAN's vision is to accelerate progress on key aspects of smart grid policy, technology, and investment through voluntary participation by government in projects and programs. ISGAN activities focus on 5 principal areas: policy standards and regulation, finance and business models, technology system development, workforce skills and knowledge, user and consumer engagement. ISGAN facilitates dynamic knowledge sharing, technical assistance, peer review, and project coordination among its contracting parties. The ISGAN value proposition relies on conferences and workshops, policy briefs, discussion and technical papers, casebooks, and webinars. Within ISGAN, the ISGAN Academy offers the ISGAN community means of rational and continuous technical skill complement and update in the field of smart grids. The Academy is proposed as a set of e-learning and training core modules dealing with the entire value chain of smart grids. Webinars co-hosted or organized with the Clean Energy Solutions Center. The webinar that we are hosting today is entitled Optimizing the Value of Storage in Power System and Electricity Markets, the SMart4RES project. This webinar will provide an industrial view on the role of storage and discuss the related utility needs and expectations presenting the different SMart4RES use cases. The webinar will also focus on the joint optimization and dispatch of renewable energy sources and storage from different angles. Finally, the webinar will present the activity addressed in the SMart4RES project regarding the dispatch of renewable energy sources and storage in isolated power system, including ancillary service provision. The speakers of today are Maria Ines Marquez from EDPD New R&D, Dimitrios Lagos from ICCS N2A, and Simon Kamal from Mine Paris Tech Armin Saint-Perse. Please use the question and answer tool to pose your question. The speaker will answer at the end of the presentation. The recordings of this webinar will be available through the ISGAN YouTube channel. Now, I leave the floor to the speakers. Thank you.
Hello, I am Ines from EDP, and I will start by presenting you SMart4RES project. I will then talk about the industrial view on the problematic and role of storage, and EDP needs and expectations as an utility. And then Dimitrios from ICCS will present you the optimization of storage operation in power systems with high renewables penetration, and Simon from Armines, the optimization of storage and renewables participation in electricity markets. So about SMart4RES that I'm going to present you now. SMart4RES is a new collaborative research project aiming to give a new rise to the renewables forecasting technology through some disruptive disruptive ideas and by a multidisciplinary consortium. This consortium joins together 12 partners from 6 different countries, among end users, industry, research, universities, and meteorologists. Smart4RES vision is to have science and industry closely cooperating to achieve outstanding improvements of renewables forecasting by considering the whole model and value chain. So renewables forecasting is today a major technology and with operational tools and services used by different actors. However, these have several gaps and bottlenecks in the value chain. For example, renewables forecasting accuracy remains low, and because of this, new needs emerge. And that's why Smart4RES projects emerge to respond to these needs. The improvement of renewables predictability through an holistic approach that covers the whole model and value chain related to renewables forecasting, from weather prediction to the end-use applications. That's why we have this multidisciplinary consortium. Today's episode 5 will focus on power systems operation planning, as you can see here highlighted in yellow, and electricity markets. Dimitris and Simon will talk about this in more deeply today. I highlighted the 3 Smart4RES major objectives that are more related to this, and which means an increase of at least 15% in renewables forecasting performance and to enhance value in applications thanks to this holistic approach of Smart4RES. Beyond research and demonstration, the integration of storage assets past industrial deployments. The aim here today is to showcase EDP as an industrial actor with industrial problematics arising in the scope of storage. And today, operators of storage assets are lacking industrial tools for optimization of storage in grids and markets. And Smart4RES can help here with forecasting and optimization solutions for integration of storage in the grids that Dimitris will talk to you about, and with forecasting and optimization solutions to optimize market participation that Simon will talk to you about. So our objective today is to talk about the emergence of these new needs, more specifically about optimizing the value of storage in power systems and electricity markets, as stated for today's episode. I will now present you the industrial view on the problematic and role of storage and EDP's needs and expectations as an utility. I'm only sharing with you some developments from EDP on storage. This is a non-extensive overview of several projects and products being developed. And among several others, we are developing now storage through European funded projects, other EDP funded projects, some commercially available products and solutions, and investment in different companies and startups. These are leading to our target of 1 gigawatt capacity by 2026 on energy storage. I would just like to highlight here Kobadin, where we have a demonstrator at Smart4RES project. It is a wind power plant with 26 megawatts combined with an AC coupled lithium-ion battery. Last year, 2020, EDP had 24 gigawatts of total installed capacity, where 79% corresponded to renewable energies. So we have here a high renewable system, and this increases the needs of flexibility and reliability. And to respond to these needs, EDP is tackling several challenges, which I represented in this image into 4 main vectors: the holistic approach to address renewable forecasting accuracy, the performance of the batteries, dispatch of different power sources, and the isolated power systems reliability. Starting by the holistic approach, to enable near 100% of renewable penetration, the challenges are the forecasting errors, the undispatched energy, and the variability of the production. EDP is addressing this through Smart4RES project. We are developing here 2 use cases and managing Cobbadin wind farm in Romania, here focusing on operation, which is the critical part for EDP, has an utility. About the 2 referred use cases that are being developed at Smart4RES project. These are about data-driven bidding strategies for renewables and storage, and optimized dispatch of renewables with storage. These 2 should ensure coherence between bidding and dispatch for multiple markets, like futures, aheads, intraday, ancillary services, and with the objective of maximize market revenue and minimize deviation penalties. Simon from Arminius will present you these in more detail later in the webinar today. About managing Cobbadin wind farm. This is a hybrid system, battery energy storage systems embedded in Cobbadin wind power plants, where EDPR aims to study and test applications for energy storage in combination with wind power generation. Smart4RES is using this hybrid system with the objective of study the system capacity and minimize the energy deviations between market bids and real-time generation. Until now, as main lessons learned in Cobbadin, we know that it is important to clarify storage limitations due to the battery manufacturer restrictions about operation and data handling. The energy management system detailed definition is very critical, since the system behavior mostly depends on it, on their commands and control. And it is essential to perform different cost-benefit analyses to estimate the optimal theoretical sizing of the system. Then about the other vector that I initially referred, the performance one, about to improve battery performance and system operation. Challenges are the battery degradation, electrochemical batteries constraints, and the possible unavailability of hybrid systems. EDP is addressing these through a project, Global BAT project, where it's performing the laboratory validation and business model of nickel zinc battery prototypes for grid applications and preparation for production. This should be a novel and promising battery chemistry, a rechargeable nickel zinc battery, and should have a very high energy and power densities at low cost. The other vector about how to dispatch into different power sources. Challenges are the market regulation and developments, the undispatched energy, and the high share of variable renewables. EDP is addressing these through SysFlex project, where it's coordinating a virtual power plant in a Portuguese demo with flexibility resources and finding the right blend of flexibility and system services to support secure, resilient transmission systems. And is having storage as a resource of flexibility to support a very high share of variable renewables. This is only an illustrative image of this VPP referred that is combining different units outputs and to act as a single unit. About the reliability of isolated power systems, challenges are the decarbonization and smartification of islands, the requirements for storage and VPP in islands, and specific conditions for islands, like the usage of fossil fuels, seasonality, and non-controllable renewables. EDP is addressing these through IANO's project, and is coordinating this project and leading storage and VPP demo in an island of Açores, named Terceiras Demo. This IANOS project is developing integrated solutions for the decarbonization and smartification of islands and increasing islands' energy and resource efficiency. Since Smart4RES is using a holistic approach, is leading the developments in all the other referred vectors, and is leveraging results of the associated projects, like in the vector performance, for example, where Smart4RES is contributing with the optimization of renewables and storage operation. In the vector dispatch, where Smart4RES is helping in the improvement of the forecasting accuracy and enabling near 100% renewables operation. And in the vector isolated power systems, where Smart4RES will support the storage and predictive management of grids. Dimitris from ICCS will now present you the isolated power systems and how to optimize storage to ensure safe systems operation.
Thank you, Ines. I hope you can see my screen now.
Yes.
Okay, I'm Dimitrios Lagos from ICCS and the National Technical University of Athens, and I'm going to present to you about the optimization of storage operation in power system with high renewable penetration. We mainly focus on non-interconnected islands and how to mitigate the security concerns with storage and renewables ancillary services, and how to minimize costs and ensure security under those circumstances. In Greece, 50% of the population lives in non-interconnected islands, and those systems account for almost 40% of the total annual electricity consumption. There are 60 non-interconnected islands in Greece that form 32 isolated electrical systems, 31 micro-isolated systems, and one small isolated system, which is the island of Crete. Those islands have high seasonal variability in their demand, with peaks appearing in summer due to tourism. The energy in these islands is supplied by autonomous power stations that mainly run on diesel generators that run on light fuel oil or heavy fuel oil, which can lead in high production costs. In some islands, it could be 6 or 7 times higher compared to the system marginal price in the interconnected Greek system. And also there is severe constraints in the exploitation of the renewables in those systems that come from the technical minima of thermal units or a dynamic penetration level limit that is imposed for frequent security purposes. Therefore, there are several smart island projects that are under development that consider the installation of battery storage technologies and aim to increase renewable penetration beyond 60%, ensure the security of power supply, and minimize the impact of thermal production. However, operating the systems in high renewable penetration comes with several technical challenges. For example, there are some issues in short-circuit protection that have to do with the coordination of fault rate-through requirements and protection schemes, and also the reduced short-circuit current levels that inverter-based generation provides. Also, there are frequency stability concerns that have to do with the further decline of the inertia by when we introduce in the system power electronic generation, and the frequent and severe power imbalances that could occur due to the high variability in production of renewables or their higher probability of disconnection. For example, if the fault rate-through requirements are exceeded during a fault, or if a wind speed of a wind turbine surpass the cutout speed threshold. Therefore, in this system, the battery ancillary services are crucial to the system security, especially in high renewable penetration levels. This is now I will present a simulation of an actual Greek island, Astypalia, which aims to include the storage and achieve high renewable penetration levels. And a scenario here with 60% penetration, mainly provided by a wind turbine. And there are two cases. One is the current case where two diesel generators are running, and the case where instead of a diesel, we have a battery unit providing advanced frequency containment reserves and emulated inertia. For the same contingency, the frequency transient with the battery is less severe, both in frequency to avoid tripping of under frequency load shedding relays, but also in the rate of change of frequency that could avoid tripping of islanding detection relays that could lead to a disconnection of distributed generation. The frequency containment reserves of batteries or renewables or any other inverter-based generation can be provided through a power frequency characteristic. For renewable units, if the system operator wants them to participate in frequency containment reserves in under frequency events, they have to be deloaded and not operated at their maximum power, because there have to be a surplus in order to assist in frequency regulation. But they can always assist on downward frequency containment reserves, dynamically curtailing their power according to the same curve based on the measured frequency. It's also a critical aspect also is the speed of the provision of these reserves. In some codes it is identified. For example, in Great Britain, there is a fast frequency containment reserve service that requires from the units participating in it to deploy the reserves in less than 1 second. This, however, might be insufficient for islands. For the same contingency that we saw previously, we tested different responses for the battery. We saw, of course, with the faster response that the frequency transient is mitigated, but still the rate of change of frequency could have a severe transient. So this severe transient in rate of change of frequency have mainly to do with the decline of the physical inertia in the system. To mitigate this effect, inverter interface units can offer a synthetic inertia or a virtual inertia service, where they modify their power basically according to the measured rate of change of frequency in order to simulate the physical inertia. Also, there could be the option of the installation of flywheels with synchronous condensers to add the actual physical inertia in the system. But with this service, also renewable energy units can provide this service, either by curtailing their power or using stored energy, for example, kinetic energy in wind turbines. And to show the importance of this service, we have, for the same contingency, the battery operating only with fast frequency containment reserves, and the second case also with virtual inertia. And we see that it can have a much faster response that can lead to less severe frequency transient and less severe rock-off transient. Also, frequency restoration reserves are also important to be provided by the battery system, because during high renewable penetration scenarios, the operating thermal units might have insufficient reserves. This case is presented here with blue. This is the case where, for the same contingency that presented previously, only the diesel units provide automatically FRR service, which leads to their maximum loading, and they are unable to restore the frequency to its nominal value. This is avoided by providing an automatic FRR also with the battery, that then the frequency is restored, and also there is a better sharing of power between the battery and the generator. So a question is how to integrate these services in the economic functionalities of the system. Right now, in economic dispatch of islands, the security is satisfied through a dynamic penetration limit of renewables, for example, 20 or 30% of the demand. The upward FCR is selected based on the island characteristic and mainly the variability of photovoltaic and wind turbines, where the downward FCR as a percentage of load. However, this approach does not include the fast-acting nature of inverter-based interface, inverter-based generation compared to conventional thermal units, and also how the uncertainty in RES production could affect the different levels of reserves. To include the services of the inverters, one approach is to use a simple representation of the physical equations, in that the fast frequency containment reserves of the batteries can be modeled through a ramp model that is a faster ramp compared to the thermal units frequency containment reserves. Their synthetic inertia service can be added to the total inertia of the system, which has also the thermal units inertia, and both of them can be included in a simplified representation of the swing equation to have and use then some techniques to derive linear constraints that correlate these services with frequency metrics like Nadir, Rokov, or steady-state frequency. There are several research work that does it. I have one cited here. To present what is the benefit of using this analytic approach, we have run the economic dispatch for a small island for 3 days with 20 minutes interval. And this economic dispatch, we either use the current practice to calculate the operating point and the reserves, or an analytic calculation. Every economic dispatch operational point was also fed to a dynamic simulation model of the system, where the contingency of the largest RES unit was applied. And using the current practice, we observed that in several scenarios, the desired Nadir limit is surpassed, which is avoided when we use an analytic calculation of the reserves in the economic dispatch problem. Also, non-interconnected islands are small systems with renewable generation located in close areas, and they also supply the limited amount of customers. That can lead to high load and renewable forecast errors compared to larger interconnected systems. And those errors could lead to lower acceptability of renewables in the system, under overestimation of the reserves, suboptimal use of the battery, and increased costs. And in SMART4RES, what we aim to do is to create and apply novel forecast techniques to improve the forecast of renewables and load, and study also their impact in the operation of small isolated systems. For example, here are some preliminary results about an advanced probabilistic forecast of renewables and load that is fed to a stochastic frequency constrained economic dispatch, which can then ensure the constraints on different scenarios and not only on the deterministic case. And we have seen that there is a decrease in costs, like 4.5%, and also an increase in renewable penetration compared to a case that we use a deterministic forecast and a deterministic economic dispatch. To sum up, there are several islands that consider pilot projects with battery storage and high renewable penetration. In those systems, the battery storage services are crucial to ensure operational security. And these services have to be included in a more detailed manner in the economic functionalities of the system to ensure the security of the island. Also, RES and load forecast could have increased errors, and this should be addressed with novel techniques in their forecast, but also in their economic optimization. And finally, I have to also add that this multiple provision of services is also important for larger systems, where also they can participate in different markets, and their of the overall battery and the overall hybrid system needs to be optimized. And Simone is now going to present to you about this subject. Thank you for your time.
Okay, thank you very much, Dimitris. So yes, now I'd like to present you the last part of this webinar on the optimization of the participation of storage in the electricity markets when they are combined with RES, so renewable energy sources. So let's consider here mostly hybrid systems. I'd like to show why forecasting is crucial for this type of optimization first. We'll discuss also how we can maximize the overall value of this system, so RES combined with storage, when we have to consider the uncertainty associated to the forecasting, the predictions. And finally, how we can deal with the specific challenge which is crucial for battery, how we can minimize degradation while providing a successful level of control. Okay, so the modeling chain of the trading strategy of RES and storage is composed of a series of steps. The first one is actually how can we invest in the good size of storage when operating combinedly RES and storage. And then we have a series of steps related to the operation of the system. And we'll see here that all those steps are actually heavily dependent on forecasts. So the first step would be to optimize the offer on the market. This can be done either at the day ahead or intraday horizon. As we've discussed previously, we want to offer multiple products because it's quite known that just using storage for provision on the energy market is not enough to return on investment. So we have to provide multiple products, multiple services. And then closer to real time, we'll need to optimize the dispatch, the control of these multiple products. And finally, evaluate those. So what I want to stress here is that forecast has a central role as an input for the offer, but also the control. And before that, I would like to talk to you about the sizing challenge. So obviously, when you size a storage system combined with RES, you do it based on the optimization on the return on investment, considering the potential values of the different products. But there is one aspect that is quite frequently overlooked, and this is the impact of the forecasting error on the sizing of the storage. So actually, a very important aspect is that the forecasting error on renewable production is often autocorrelated. That means that the error that we make is correlated in the successive time steps of the forecast. We have one example here in the center. So we have a prediction in light blue of wind power of a given wind farm. And it actually anticipates an upward trend, an increasing trend in the wind power production in a 30-minute interval, but it does it a bit too late based on the observed measurement in red. This is due to probably an inherent error on the weather forecast used for this model. So what's the result is that on this overall 30 minutes, we have quite a large area here depicted in this shade of blue, which is the cumulated forecasting error. And you see that if you underestimate the production at time t, then at time t+1, t+2, and so on, you do the same error. So the result is that the cumulative forecasting error is large. And if you want the storage system to compensate these errors in order to meet the initial offer, which was based on the prediction, then you need to, in this example, charge continuously the system. So the impact on the sizing of the storage is quite natural. The larger the cumulative forecasting error is, the larger the energy capacity of the storage size needs to be. So we have to incorporate this in the optimization of the storage sizing. And if you are interested, I refer here a specific paper of a previous work we've done. So you can relate to that if interested. Then if we move to the offering and control stage of the modeling chain, then we have to take into account the uncertainty associated with this prediction. This is because you want to know the level, the cost that would be associated by any level of production. So one way to do it would be to derive these probability densities you have on the left for different time steps. But if you do this independently from different time steps, then it won't inform very much on what is the transition in terms of uncertainties between those two time steps. So it's not very useful, for instance, to optimize the schedule of the state of charge of a battery. What we need to do is to be able to do this probabilistic forecast, but also integrate the temporal correlation between those uncertainties. So typically this uncertainty at 1 hour and 2 hours, so 1 hour after. One way to do this is shown on the right. What we can do is actually derive scenarios, so trajectories that are temporally coherent. So this results in these scatter plots of points between the expected wind power at time 1 and time 2. Obviously, this is a bit costly then in terms of computation. You see that you have multiple points if you want to scan well the uncertainty region. What you can do is actually to simplify this and just take the envelope of these scenarios and then use it in an optimization model. Now that you have those either scenarios or uncertainty regions, you can incorporate them into an optimization models in order to derive your optimal strategies. So the decisions will be optimized based on this description of the uncertainties. It's important to remember that this uncertainty variable is actually dependent on the weather or the market conditions, if you consider also probabilistic forecast of prices. And this has actually a direct impact on the way that storage systems will be scheduled or the decisions will be made. You have an example here below where we compare the decisions on the state of charge schedule of the battery with an optimization in red where we don't consider the uncertainty associated with the prediction, and on no, actually on the red it's with the uncertainty, and on blue it's without the uncertainty. So what we see is that when we incorporate the uncertainty in the red curve, we are actually able to track better the case in the middle of the day where there is a high probability that the forecast of PV production is low. So in that case, we need to discharge the battery to compensate. And this phenomena will not be anticipated by the optimization in blue without uncertainty. So this is quite important because you can then increase your average revenue in many cases, but also reduce the variability of your revenue. Here again, there is a paper if you're interested to know more about this. Now, Ines has presented you this hybrid system of Cobadin in Romania, so where we have a high storage on site with a wind farm in order to provide energy, but also multiple services. So here we face quite a crucial challenge, which is to optimize our market participation on all those markets, but also to minimize the degradation of the battery, because we know this is quite key to achieve profitability of the investment on storage. So here, the first challenge is to how can we incorporate easily the cost of degradation of the battery? We know this is quite complex. So in the work in Smart4RES, we propose the linearization of this cost so that we can then implement some standard optimization techniques based on linear programming. But here my message is more on the role of the storage, of the forecast on the problem. So actually we see that we need forecast of renewable at multiple timescales. We will need a forecast at the day ahead horizon to derive the offers. And then our multi-objective approach, so optimizing both the cost but also the degradation, will be applied also to the control. And then we will need a second type of forecast, which is an updated forecast of the renewable production at the intraday horizon, so typically for the next hour. And what we have been observing in this context of the control is that the quality of the forecast of RES production is really key to achieve an efficient control of the system. So what we've been doing is to make a perturbation from the initial RES forecasting that we had at the day-ahead stage. So the further you go on the right, the worse the forecast is. And what we observe is that the error on the controls, on the tracking, is actually non-linearly increasing with this decrease in quality of the forecast. And this is true both for the market offer, so this means we'll have more penalties to pay, but it also means more error on the tracking of a reference state of charge for the battery. And this will translate into more degradation of the battery system. Okay, to conclude on this part, we've seen that, okay, forecast is key for the optimization, The only problem we have if we want to implement a forecasting of all the uncertain variables on this type of problem is that the resulting modeling chain is very long, it's quite complex. So if you consider that you gather all the data on the renewable, on the storage, on the markets, you have to forecast the RES production first. So as we've seen, at least at the day ahead, and probably also at the intraday horizons, you have you can have two models for that. Then you have to forecast the prices on the energy market. So here also at least 2 or 3 models for each price for the day ahead for the imbalances. The same for the ancillary services. So if you have several ancillary services, frequency containment, AFRR, you need at least 2 models per market. So you result in a dozen of forecast models easily for the different quantities that have to be incorporated in your trading strategy. So this is a bit hard to maintain and to develop. So what we do in Smart4RES is that we are developing data-driven business tools that incorporate all the uncertainties into a single model. So we bypass the need of having those multiple forecast energy markets. And our objective is to obtain, let's say, the same revenues, the same performance than with the classical chain. And we will present this in the next webinar. Okay, so I conclude with some take-home messages from this webinar. So with the presentation of Ines, we've seen that utilities such as EDP already implement storage, and they have multiple R&D activities to ensure that storage is providing the expected levels of flexibility when coordinating with the renewable systems. On our side, it was quite clear that the forecasting accuracy is crucial for the sizing of the storage, but also the performance of the trading strategies. The degradation of the battery needs to be minimized and incorporated into the optimization models. And this can be done in 2 ways. So Ines mentioned that you can work on the materials that are used to build the battery, but you can also incorporate the model of the degradation in your predictive control. And the last point is that storage is able to provide a series of ancillary services so that isolated power systems, such as non-interpolating ions, are able to work in a stabilized way, even under a high penetration of renewables. Here are the references that you will be able also to look after later. So on behalf of all the authors, I'd like to thank you all for attending. This series continues. We'll have in next year another webinar focusing on the integration of RES forecasting into the modeling tools for electrical grid. And yes, please, we'd be happy to discuss if you have any questions. Thank you.